Hello, everyone. Good morning. Well, it's good morning to me. I don't know about you. I'm going to present about this project that I'm working on for the last half year, together with the Lava team. When I started contributing back to the team, I thought it was going to improve Android testing, but now I realize it not only improves Android, but also all the areas of Linaro work that are going to be tested on Lava are going to be impacted by this. And that's why I'm planning to present today. A little bit about myself. I'm a software engineer at Linaro. I used to work on Squad. Now I'm working on the Lava team. I'm a long-time free software developer. I'm a member of Debian. And I also am drive-by patch contributor to lots of projects. So lots of one-time contributors to several projects. And then our agenda today, I'm going to give a very brief introduction to Lava so that we understand the context in which this work is being done. I'm presenting the use cases for using Docker in Lava. I'm giving an overview of the current solution where we are using LXC and the problems with it. I'm giving an overview of the new solution based on Docker and present the current status of its deployment in Lava itself as an upstream project and in the Linaro labs. So a brief introduction to Lava. Lava stands for Linaro Automated Validation Architecture. It's basically a test execution system. So it has the goal of running testing software on real hardware. So it includes deploying operating systems to the boards, booting them, and then running tests. It has several usages. It's used by kernel CI, for instance, for doing boot testing. LKFT is a Linaro project that does system level testing. So we test mainline kernels and LTS kernels against several use cases and report that back to the kernel community and to Linaro customers who use that project. It can also do power consumption tests, benchmarks. It also supports running multi-node tests, which are tests against multiple devices, so you can test communication between them and other types of inter-device testing. So Lava tries to automate testing, the type of testing people usually do manually with development boards on their desks. So when you're doing this type of development, you have to, the developer has to control power somehow. So maybe people are unplugging and plugging boards, but maybe they have power relays that are controlled remotely. Then that's how they turn on and off the boards. They have to have a way of getting to the serial console on the board. So usually people use serial relays or even direct serial connections. Then you have to control the board to download the kernel and a root file system from somewhere. And then you run the board, then you get a shell on it, and then you run your tests, and then you power off the board and start things all over again. And the point of Lava is automating this. So you submit a test job configuration, which includes, among other things, the software you want to run on the board. So it can be a kernel, a DTB, a rootfs. And there's a machine that controls each board, which in Lava terms, we call it a dispatcher, which will control power, serial connections, will control how the software is provided to the board. It can be via NFS or TFTP or any other methods. And that's going to automate the manual work we usually do with development boards. So in Lava, we have a server, which is the component that receives the job definitions. And we have one or more dispatchers, which are the machines that are actually connected to the board, that you have the power control, the serial relay, you serve files to the board, and so on. And the use case we want to solve here is running arbitrary code on the lab infrastructure. So by definition, you can already run arbitrary code on the test boards, because Lava has the mechanism to recover if your arbitrary code does something wrong. So if your test switch crashes the board, Lava is able to recover it. If you flash a bad kernel, Lava is able to recover it. But then if you do that on the lab machines, first the lab people will not be happy at you, and then we'll have to manual work to recover the lab. So that's not good. So for some types of testing, we want to allow users to run arbitrary code, but we also don't want them to run arbitrary code on our infrastructure. So there's going to be a middle ground there. So today, some of the use cases that use this functionality is, for instance, Android testing. So a lot of the Android testing with CTS and VTS involves running tests from a host machine that runs ADB, fastboot, etc., and connect to the device under test. And that's one of the use cases we want to support. We want to support people running their own ADB and fastboot binaries. Maybe they are testing the latest Android development kit, or maybe they need some feature that's not available yet in the binaries we have in the lab. So that's another use case. Another use case is manipulating downloaded images. For instance, you usually need to include kernel modules into the rootfs you are building. So you don't want to rebuild a new rootfs with every kernel. Instead, you want to just get the kernel modules for that kernel and inject that in the rootfs. So that's something you can also do if you are able to run arbitrary code in the Lava infrastructure. And also another use case we are starting to support now is running custom QEMU binaries. So usually you have the QEMU binaries that are available in the lab system, but then also you are developing QEMU itself or KVM for the kernel, and you want to test that against the usual Lava infrastructure. So then you need to be able to run arbitrary binaries in the infrastructure. So right now we support that using LXC. You treat LXC basically like a regular Lava device. You deploy some file system to it, you boot it, and then you run tests. You run the code there that will both install any dependencies you need and do the job you want. And as I said, the test job needs to contain explicit instructions to install the needed software. So you want to pull ADB and fastboot from somewhere. You want to connect to the board and do your thing. This makes the job definition a little long and complex, more than is necessary. And for instance, today to run the Android test suites against a device, you need to first deploy a LXC container. So you have to declare, I want a LXC container that has this base system. Then you have to tell Lava to boot that container as if it was a regular device. Then you need to have a test definition that install the necessary tools inside the LXC container. Then you get to the real work, which is deploy the image to the device, boot it, and then run tests from the LXC container connecting to the device. And then here we have a brief comparison of LXC versus Docker. None of what I'm saying here is to badmouth LXC. I happen to be one of the maintainers of LXC in Debian, so I think it's a very nice system. is just not suited to what we are trying to do here. So LXC stands for Linux Containers. It's a system to manage full system containers. That is, those containers, they boot, they have an init system. So you have PID1 inside the container. Your regular services start as normal. So if you have a web server inside the container, it will start normally. And the whole point of LXC is to make the containers look and feel like VMs. So it's you have less overhead since you don't have to emulate a system. So you have all your processes there, and you don't have the overhead of running a second kernel. On the other hand, you have the security problems of not running a separate kernel. So there's a trade-off there. And one of the points of LXC also is that usually you only have available vanilla OS images. That is, you have a clean Debian install, you have a clean Fedora install, you have a clean Ubuntu install, and then you have to install your things on top of that to be able to use the container. Docker, on the other hand, is suited to application containers. So it executes only one application, usually with a very small fake init system. So usually you have a minimal PID1 in the container just to manage, to control the actual application that's running there. You don't have system services. So if you have a Docker container that has a web server inside, it won't start automatically. You have to manually start the web server. And you have images that are distributed with applications pre-installed. So you do have the vanilla OS images that you can base on to create your application containers, but you can distribute the containers with everything that you need already installed. And that's makes it easier to deploy applications because you don't have to do anything. You just grab the container that already has the application installed, and then you just run it. And as a curiosity, in the early days, Docker actually used LXC as the container runtime under the hood. These days, it doesn't anymore, but in the early days, there was a nice relationship of mutualism between the platforms. So now in Lava, we have Docker support. So this brings us a few advantages. One is you can use any available pre-built image with the dependencies already installed. So you don't have, again, to start a container and then install things in it. You just grab the image that already has the things you need installed. And it also lets us have a lot shorter test definitions in Lava. So the test definition to do the same thing using Docker is a lot shorter than the one that does the same thing on LXC. So we will have examples ahead. So we support those use cases that I mentioned in the beginning. So you can run ADB and fastboot inside Docker for deploy, boot, and test, because you want to run custom ADB and fastboot binaries, because you want to run the very latest Android development kit, or for any other reason. And that's available since Lava 2020.02, which was the latest release of Lava. You can manipulate images after download, so which is what LKFT does today. We have examples of all of them later. So that's merged into the master branch, and it will be available in the next release, which we are working on it these days. So it'll be available very soon. And also the custom QEMU binaries, the support for it is also merged and will also be available in the next release later this week, I think. So now I have a few examples. I didn't even bother to show the old way of doing this with LXC, because we consider that deprecated, and we want to move on to use Docker because it's simpler and faster. So first example is running ADB and fastboot on Docker. So you have a regular deploy definition, deploy action in your job definition. The only difference is that now you specify a Docker image. That's all. You specify the images as you did before with URLs to the images and their names, and then you just get ADB and fastboot inside Docker. So you have to provide your image. In this case, the example uses an image that's called ADB-fastboot, and it just works. It will run fastboot inside Docker container, and Lava will share the device node with the container under the hood, and it just works. Fastboot gets called from inside the Docker container, and it does the deployment of the images. Then to boot the device, again, same thing, you just specify a Docker image, and then the fastboot boot method for Lava will just run fastboot inside Docker, and it will just work. And for testing, also you just add the Docker image declaration, and then you have your usual test definition for Lava. The only difference here is that this test definition will run inside the Docker container and not inside the device under test. So for people testing Android, it's like before. So the test definition was running the LXC container. Now it runs in the Docker container, which with the difference that it's faster and it's simpler, because you can have your container, everything you need already installed. You can even have the test suites themselves inside the container again already. And then you just specify a test definition that will run inside that container and will start the test for you. A second example is manipulating downloaded images. LKFT uses this today with LXC, and the job definitions are more complicated than necessary. And now we are able to migrate to this new way of doing things. We have now a new deployment method called downloads. So you specify the image you want to download. So in this case, we have a kernel, we have a modules, tarball, which was built together with the kernel, and we have a rootfs. In this case, the rootfs is some fixed rootfs you want to use for all the jobs, and the modules are the ones that were built together with the kernel you are using for this test. And then you have now a post-process section for the deployment, where you specify the Docker image you want to use and what commands you want to run in the Docker image. In this case, we are in this example, we are using Keer, which is a tool developed by the LKFT team, which does this merging of images. So it will, for instance, take the rootfs image and inject the kernel modules inside it and generate a new image with the rootfs already pre-populated with the kernel modules. And then it modifies the files in place where they were downloaded. And then you do a second deploy to the device this time with two differences. You specify you want to do the deployment from a Docker image, and you want to get the images from the downloads protocol, which is a fake protocol we have in Lava now to access those files that were downloaded in the previous step. So you downloads, you do any post-processing you need with the images, and then you can refer to them later in the test job by using the downloads pseudo URL scheme. then you can get your, in this case, you see here boot.image and rootfs.image were files that were created by the post-processing in the previous step. And the third example is running a custom QEMU binary. It's very simple as well. You just use the regular QEMU boot method and you specify a Docker image. So if the Docker image runs the QEMU binary by default as the entry point, then you don't have to specify a binary. Or if the image just has the binary and you need to call it by hand, then you pass the path to the binary, and then Lava will start the VM with that QEMU binary inside the Docker image instead of whatever QEMU binary there is in the Lava machine. So a few closing remarks. As a reminder, we have the ADB fastboot support for Docker in the first example already available in the latest Lava release. The other two will be available in the next release. And future work that they're doing in the short term, we are going to do a LXC to Docker migration guide to help people migrate their jobs over to the new Docker support. And we are also now working on improvements to Lava itself to be able to run the entire Lava dispatcher as a Docker container. That will unlock a few other use cases we have. For instance, to making it easier to deploy Lava. And that's all I had. I will open the chat window now to see if we have questions, but feel free to ask. Okay. Paul asks if all the stuff is described in the Lava docs already. So no, we are currently reformulating the Lava documentation, and we need to do an effort to document things, but they are documented in the release notes. So every time you do a release, we write some documentation for in the release notes. So if you want to use those features, you can check the release notes. They are there, and we are working on having updated docs. Larry asks, in the first test action, we install something in the container. How the second test action could share the packages which was installed in the first action? Looks like no persistent Docker container supported here. Yes. So the point is, you provide your container with everything already inside. So you don't have to install anything inside the container. So when we say here use this image, then we assume that everything you need is already inside the image. So you don't need to, you shouldn't need to install anything in the container at the job definition stage, at the Lava test job. So you provide your container with everything you need already inside. And that makes it easier because you can test your container locally after building it. And after you push that to some Docker Hub, you know that exactly what you pushed is what going to run on Lava. So you don't need to test the installation process. You do the installation process as a regular Docker container build, and then it's available. We have 1 minute to go. Any more questions?
There's another one from Stephen.
From?
Stephen Lawrence is not showing up. Sometimes host fastboot flashing is simplified into a script. Is it possible to use such a script in the new scheme, perhaps via download manipulation, thinking of deploy stage?
Yes, the step you provide for the deployment are arbitrary shell commands. So wherever you do that, you run inside the container. You already have access to the device at that point. So if you want to do the deployment yourself, calling ADB by hand from the post-processing, it's possible. We didn't think of it yet, and I never tested, but it should work.
And one last question. Drew asks, can this be used for U-boot?
For U-boot. Yes. So yeah, another use case I didn't mention is if you want to run tests against a U-boot shell over zero, for instance, you want to give no inputs to U-boot and then test that U-boot does the right thing. Yes. So yeah, I forgot to add this detail, but you have the serial connection between the Lava dispatcher and the device is also shared with the container. So you can, from the container, connect via serial to U-boot and then run whatever test you want. Yes.
Thank you, Antonio.
Thank you.